In this video, we're going to look at an example of computing a triple integral using spherical coordinates. So we're asked to compute the triple integral over the solid x squared plus y squared plus z squared is less than or equal to 9, and y is greater than or equal to 0, and the function that we're going to integrate is y squared. Alright, so x squared plus y squared plus z squared is a sphere centered at the origin with radius 3. So that tells us right away that rho has to be between 0 and 3. Now notice it tells us that the y has to be positive, but doesn't give us any other restrictions on the z value. Phi again measures the angle between the positive z-axis, from positive z-axis rotating down towards the xy plane, if you will. Since there are no restrictions on the z, our phi runs all the way from 0 to pi. And then finally, since our y is greater than 0, that tells us that if we think about it in terms of the xy plane, the region has to be above the x-axis. If the region's above the x-axis, that means our theta has to go from 0 to pi. So now we can rewrite our triple integral. We can replace y with rho sine theta sine phi, and then we square each of those individual pieces. We replace the differential with rho squared sine phi, d rho d theta d phi. Then we have our rho bounds, our theta bounds, and our phi bounds. One thing that we notice now is that our integrand is the product of three functions, each of which we can write as a single variable. I have a rho to the fourth I can write all by itself, a sine squared of theta that I can write all by itself, and then a sine cubed of phi that I can write all by itself. Also, notice that our limits of integration are all constants. So since I have the factorization property of my integrand, where I can factor it into individual functions of a single variable, and since my solid can be described in terms of constant bounds for all three variables, I can rewrite this iterated integral as a product of three integrals, and then calculate them individually. Certainly when we do an antiderivative for rho to the fourth, we get a 1/5 rho to the fifth. When we evaluate that from 0 to 3, we get 243 over 5. For an even power of sine, we need to use our power reducing formulas to be able to rewrite it. We can rewrite sine squared of theta as 1/2 times the quantity 1 minus cosine 2 theta. Antiderivative for that is theta minus 1/2 sine of 2 theta. When we put in 0 or pi in for theta for the sine piece, that's just 0. So this just turns out to be pi over 2 when we evaluate at the endpoints. For sine cubed of phi, we need to pull off one factor of sine for the du, convert the rest to cosine, so I can rewrite the sine squared remaining as 1 minus cosine squared. Antiderivative here, we need to do a u substitution. If we let u equal the cosine of phi, then du will be negative sine phi, so that's where this negative comes from. Antiderivative will be u minus 1/3 u cubed, but u was cosine of phi, so we get cosine of phi minus 1/3 cosine cubed of phi. Put in pi, put in 0, rewrite, we'll get 4/3. So when you multiply all those pieces together, you should get 162 over 5.